Hello and welcome to this short clip going through some of the chemistry of the halogens. It's designed to be viewed once you've done some independent study from your textbook or made some flashcards already, so make sure that's all to hand before we start. So the first thing to notice is the electron configuration always ends in p5. This is reflective of the idea that they need to gain an electron to achieve a full p subshell. The boiling point also increases as you go down the group. What's happening here is there's more electrons in each atom, as you can see from the electron configuration, so therefore you get more and stronger London forces, meaning more energy is required to overcome these. So although the individual London forces tend to be weak as a general rule, the larger the atoms, the more the electrons, so therefore the larger the instantaneous dipoles that form, which leads to stronger London forces. So one of the key things about halogen chemistry is they undergo displacement reactions with each other. And on the table on the screen you can see some of the colour changes you'd expect if you mixed the equivalent halide with halogens. So we can assume that if we look at X and Y as two halogens, Y being in the form of a halide, X is a better oxidizing agent than Y. X has removed an electron from Y minus, and therefore Y2 has been formed. So if you remember back to our work on haloalkanes, and when we looked at rates of hydrolysis, we were using bond enthalpy of the carbon-halogen bond. So you can probably see the connection where the bond enthalpy decreases as the size of the atom gets bigger, so therefore its electronegativity gets weaker. So therefore good candidates for being an oxidizing agent would be things like fluorine or chlorine, and good candidates for being Y, in other words being oxidized, is maybe bromine or iodine. So another way to do displacement reactions, which is a little bit more visual perhaps, is to shake the halogen and the halide together with some cyclohexane. So the lower layer is aqueous, whilst the upper layer is organic, and the solvent is usually something like cyclohexane, and that will contain the halogen. And the explanation is that the displaced halogen will dissolve more effectively in an organic solvent due to London forces. So if you give them a shake and then allow the two immiscible layers to settle, the halogen will be revealed by the colour of the upper layer. So another aspect of halogen reactions is something called disproportionation. Although it's not exclusive to halogens, it occurs elsewhere in chemistry as well. It's a unique type of redox reaction where you get simultaneous oxidation and reduction of the same element. So you can see quite clearly from the equation that this has happened with chlorine. So we also get this when chlorine reacts with water. So you get two acids forming when chlorine reacts with water. So if you put the oxidation states above all the elements, you can see clearly that there's two separate things that happen to each chlorine atom. You have oxidation and also reduction. So this brings us on to the subject of chlorine in drinking water because it reacts with water. So if we take the HLCl species, this is called Hypochlorous Acid, and basically it's the chlorate 1 ion. So the chlorate 1 ion has chlorine in the oxidation state of +1, hence the chlorate 1 name. And chlorate 1 is very toxic to microorganisms, so it's added to the water supply in small amounts. And this is to guard against waterborne diseases. But we also have some evidence that chlorine reacts with organic matter in water to create small amounts of carcinogenic haloalkanes and other compounds. And chlorine itself is toxic. So as you'd imagine, even though it's added for a good reason to try and protect us from waterborne diseases, not everyone is happy with not being able to choose whether they drink chlorinated tap water or not. there's several issues surrounding it. And also looking at the chemistry, there's several aspects to the chemistry of halogens. So what we're going to do now is have a look at an exam question. So looking at the question, it asks you to state one advantage and one disadvantage of using chlorine in water treatment. So in order to keep things simple, here's how I'd suggest going about this. So the advantage is that it kills microorganisms, and the disadvantage is that it's toxic. So the next part should be fairly straightforward because we looked at that a little bit earlier. So not forgetting, of course, that they're now asking us about bromine, not chlorine. Move the page down a little bit now. And it says displacement reactions can be used to detect bromide ions in solution. So notice how they're switching from bromine to bromide ions. So it explains what this student does. She bubbles some chlorine gas through a sample of the solution and the mixture changes colour. After that then she adds an organic solvent, cyclohexane, to the mixture, and she shakes the contents and allows the layers to separate. So remembering our experiment from earlier that we talked about, it's asking you now to write the ionic equation for the reaction that takes place in step 1. So remember that it's chlorine gas and bromide ions. So remembering also it's a displacement, so you need 2 bromide ions to give you 2 Cl- and Br2. Then it asks you what colour does the cyclohexane layer turn in step 2. And seeing as bromine is orange, as you can see from the photograph, that's the colour you need to put down. So in this next part it gets a bit more challenging. It says chlorine reacts differently with dilute and concentrated aqueous solutions of sodium hydroxide. This is new information. So that must mean we're now looking at application as opposed to a simple recall. So then it says in each reaction chlorine has been both oxidized and reduced. If you remember, we mentioned very briefly the idea of disproportionation. So that must mean that's the answer for part I. So that's simply remembering what the term is called. So it says an element is both oxidized and reduced. That's straight from our definition we talked about earlier. And it says write equations for these 2 reactions of chlorine with sodium hydroxide. So let's highlight the word dilute and look at what it tells us. It says when chlorine reacts with dilute sodium hydroxide, one of the products is sodium chlorate 1. And we talked about chlorate 1 a little bit earlier. So the question tells us essentially that much already. So now what we've got to do is try and put together an equation that represents disproportionation. So quickly using the oxidation numbers in sodium chlorate 1, this now allows us to produce another species. It doesn't say how much sodium hydroxide we need to use yet. So we've now got chlorine in +1 and chlorine in -1, so it's disproportionated. So now we need to find a way of creating 2 sodiums. So clearly we can double the number of sodium hydroxides on the left. And the spare atoms can be used up by creating water. So the next one is concentrated sodium hydroxide. So the question tells us this time that chlorine is reacting with sodium hydroxide to make NaClO3. Now again we have to disproportionate because it says that both of these are disproportionations. So again we can use NaCl and also water. Now we think carefully how we're going to do this because we've got 3 oxygens on the right and we've got 1 oxygen on the left. So a little bit of balancing and thinking required here to make it work. That's why that took 3 marks, with a bit of thinking time there. So finally it says it forms another chlorate called sodium chlorate V11. Now V11 in Roman numerals, that means 7. So we have to put a sodium chlorate together that has chlorine as +7. The way we do that is to use the more electronegative oxygen, and so we put more oxygen atoms in to make sure chlorine has to take the ever more positive oxidation state. So the only way we can do it is to put 4 oxygens in. Okay, so hopefully it's a fairly useful introduction to halogens, plus a look at a question that takes you around all the various parts of halogens. So for now, thanks a lot for listening, and until next time, see you soon.